Hi, this chapter is about repeated game. You know, for the next week and next week, I'm going to give you my comment about your proposal so that you can upgrade your paper. What meant actually proposal. So when this chapter is over, I mean, I'm not going to give you this kind of general types of lecture more. So let's see. And as I said, by the next, I mean, in the 15th week, you are supposed to send me your proposal, final version, and also you should post um, 20 or 30 minutes of a video clip, which is about your presentation. Okay, um, so you need to prepare about that. I mean, you don't need to do a lot of things, but you just um, present your idea as I just do here like this. So there are lots of applications that you can do that. So I mean, you're supposed to do that anyway. Um, okay, repeat it again. So let's think about these general types of prisoner's dilemma scheme. I'm not going to talk about what is the meaning of prisoner's dilemma scheme, just to look at and focus on that table, normal form game. Here are two players, player 1 and player 2. If they cooperate, then they will get 9-9. If they deny together, they will get 5 and 5. And if one guy is deny and if one guy is cooperate, the guy who denied get 10, while the guy cooperated get just 1. So as you can expect, because this is a structure of a prisoner's dilemma scheme, here the best response is this. Here the best response is this. And if player 1 cooperates, the best response is this, and the best response is this. As you can see, only one equilibrium, Nash equilibrium is deny and deny. Deny is only a unique Nash equilibrium. But if you look at the result, this result is not optimistic because if both cooperate, their payout, social payout is 18. But here, social payout for these two persons is 10. This is 11. This is 11. So in terms of the social efficiency, actually the worst scenario here is that they are both choosing D9. But the best scenario for them is to cooperate for in terms of society. But because they focused on their own egoistic payoff, at the end of the day, they choose the worst scenario. This is a little bit different from what Adam Smith said. Adam Smith said that um, you know, because if all people focuses on their own egoistic payoff, then at the end of the day, the society's well-being will be maximized. However, if we look at this, you know, even though they are just focusing on their own payoff and just choose the which maximize their payoff, what reaches to is that they are just choosing denying and denying. That's all. Okay. So how can we solve this problem, or how can we improve this problem? So, I mean, there are lots of ways, but the first way people can think, what if they are playing this game twice? I mean, in one sense, this Prisoner's Dilemma game gives people a chance to cooperate, but they didn't. But what if we give one more chance for them? Let's analyze it. By the way, in this Prisoner's Dilemma game, as all we know, players, first player and second player, their strategy both cooperate and deny, and their payoffs are here. Okay, so I mean, we also can think about profile um, space, profile set, that is a Cartesian product of these two players, that is CC, CD, DC, and DD. If the first character represents first player's strategy. Now, think about when they are playing this game twice. Actually, in order to understand what's going on, um, we call, when they are playing this game first, we call that first stage. And also we call, if they are playing this game again, we call that second stage. However, regarding second stage, there are 4 different contingencies depending on what kind of outcome was chosen in the first stage. I mean, if we just focus on stage, it's like there is just one schedule stages continuing. Maybe this is first stage, this is the second stage. You may think like this. However, um, in terms of contingency, because we are constructing the game tree will happen depending on different result. For example, in the first stage, if they are playing cooperation together, then this outcome will happen in the first stage, right? Then in the second stage, they are playing this game again. Even though the payoffs and strategies and the players are the same, however, their histories are different. If I'm drawing a game tree, if this is first stage, depending on different outcome of the first stage, it's like a different game tree is constructed. If this outcome is played, then this game will be played. This game path will be chosen, and also if they played this outcome in the first stage, then after taking this path and this game is played. You know what I'm saying? It's not something, there are 2 sequential stages, even though there are, what is realized is just one stage. However, if we think about each history or each parent or each history, it depends on what happened in the first stage. So game 3 will look like this. Here's the first stage, and in the second stage, there are 4 contingencies depending on what outcome is realized in the first stage. Okay? Try to understand correctly about this game 3. Okay. Now, think about the strategy. If we go back, just this, one-shot game with the Prisoner's Dilemma's game, then the strategy is just C or D, right? However, so if I'm representing the strategy, just C or D. However, look at this. There are 5 contingencies for each player. Each player can choose here. If this contingency is happen, this information set is reached, then each player has a chance to choose. If this information set is reached, then each player has a chance to choose. Also, when this information set and this information are choosing, then are reached, then they have a chance to choose a strategy. Meaning that there are actually 5 contingency, or maybe there are 5 times that they can choose. At the initial node, and when this node is reached, and also there are 3 nodes reached. So actually there are 5 contingency, 1, 2, 3, 4, 5. So depending on, in each information set, each player should express what kind of strategy they will play. That is a strategy. So strategy should be constructed in this sense. CCC must C, CCD, CCCDC, something like that. For example, I mean, we don't need to follow these rules, but if I'm setting up the rules like that, the first character is represent each player's action at the initial node from here. When this node is reached, for example, C, D, D, C, C, if the CC is played, then this player will play D. Likewise, if the last one is representing the strategy when DD information set is reached, then C means if this node if this information set is reached, then this player will play cooperation. Okay, so it's like the number of possible strategy that each player can has is 2 to the 5. So that is 32 combinations. It comprises like C, 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 D, C, 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 D, something like that, D, 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 D. There are 32 different kinds of strategy that each player can choose. Okay? Now think about that. Let's solve this game. Usually we solve this game with using so-called backward induction. So we try to think what is the best solution at the end of the game tree. In any nodes of the stage game, second stage, in any nodes of the second stage, the unique, there are 4 different second stage. In every kind of second stage, actually only one Nash equilibrium here is to choose deny and deny, right? DD. DD is only one Nash equilibrium that people can choose. In any second stage, in any situation, the Nash equilibrium is that both choose deny and deny, right? So 5 and 5 and 5 and 5. This is the outcome they will get no matter what kind of things happens in the first stage. This is the second stage. So no matter what happens in the first stage, they will get is 5 and 5. Okay? So think about that. What it means if I say differently, in the second stage, nothing is changed, no matter what you choose in the first stage, right? That is what second stage is talking about. So in the first stage, no matter what they will choose in the first stage, in the second stage, they will get 5 and 5. Say differently. First stage and second stage, no matter no matter what strategy is chosen, in the second stage they will get 5. What it means, first stage's choice has nothing to do with the payoff they will get in the second stage. Again, the choice of the first stage has nothing to do with the payoff of second stage, right? First stages, the choice of first stages has nothing to do with the payoff of the second stage. What it means, we can think this is not all the time true. Because that is a special types of a game, so that it happens. If we deal with different games, it does not hold in this sense. Anyway, for these special types of game, first stage's choice has nothing to do with second stage's payoff. What it means, it's like the choice each different stages seems to be independent, so that the player in the first stage can choose without considering what will happen in the second stage, so that they will choose deny and deny. Why? Because this is a unique Nash equilibrium. Okay, so at the end of the day, in any nodes of the second stage, the unique Nash equilibrium is DD. Hence, all players know that their payups in the second stage is 5 and 5. 5. It means the first stage's choice is independent with the second stage's payup. Therefore, the unique Nash equilibrium at the first stage is DD, because it's like we are playing just a prisoner's dilemma game. Therefore, the unique subgame perfect Nash equilibrium. This is a subgame perfect Nash equilibrium. Why? Because we find an action at the end of the game. So DDDD and DDDD is the only unique subgame perfect Nash equilibrium of this twice repeated previous dilemma game. And their payups is 5 in the first stage and 5 is in the second stage. So 10 it will be their payups. If we expand this idea to the finite times repeated game of the Prisoner's Dilemma game, then also we can apply this idea again. If we repeating this game, we're in the finite number, then in any cases, at the end of the stage, they will play, no matter what is happened in the history, they will play D at the end of the game. So if we keep playing this game in the finite times, then they will keep playing just D and D and D and again. So only unique Nash equilibrium of this game when we are repeating finite times, that is playing deny continuously. So what it means, if we expand this idea a little more, if we repeat a game having a unique Nash equilibrium, or just we have just only one Nash equilibrium, then the subgame perfect Nash equilibrium of that game, SPE, is to keep playing that Nash equilibrium strategy. If we repeat the game having a unique Nash equilibrium with the finite times, then the SPE is to keep playing that Nash equilibrium strategy forever. That's it. Okay. So even though what we get here, even though we playing the same game, previous dilemmas game, and again and again and again, people don't choose to cooperate. They will keep choose to deny forever. Nothing wrong there. Okay. So if we expand this idea, what if we are playing this game infinitely? When we are playing this game with finite times, we may think that this game will be over, will be in finite times. But if we are playing this game infinitely, it implies that people think that this game is not over. Okay. So strategy will look like this. It will consist of infinite number of strategies, but it's not repeating just one number of action they will choose at each stage. I mean, in the first stage, they will choose C or D, but in the second stage, they should decide what they will do at each different information set. Because there are four information sets, they will express what kind of action they will choose at each information set. So that it consists of four different actions they will choose when each different information set is reached. For example, CCCD. In the third stage, because one Prisoner's Dilemma's game generates four different kinds of nodes. Okay, so that here are four different Prisoner's Dilemma's game. 4 times 4, there are 16 different information sets they can choose. Again, each information set represents different history in the previous past. I mean, in the first stage, in the second stage, what they are playing are different. So each different information set is representing that different history. Okay? And then, so there are infinite number of strategies are here, but problem is that we cannot deal with that infinite number of realized strategy. It's too long. So instead of dealing with these long strategies, we are just, uh, gives you a rule that construct a strategy. One very famous strategy here is called the green trigger strategy. It consists of like that. At the first stage, both will choose, everyone choose C, cooperation. Okay. Then once another player deviate from cooperation, so that they are choosing D, after one player recognize that another player's betray, that player keep playing D forever. Again, this is first stage, second stages, third stage. There are many stages. They keep playing C, again C, 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 so they can get cooperation payout. If one player just decide to betray that player so that they choose D, then because one player is choosing D and another player is in C, the player which chooses D will get a lot of payout. And probably this player will keep playing D for a certain time, but after n times, let's say that this player who betrayed recognize that other player betrayed, the self. So from after recognizing that, this player also keep playing C forever and no D forever to punish those player betrayed the self. Okay, that is a called strategy, a green trigger strategy. That strategy can be realized, can be represented here in this sense, but that's too wrong. Okay. So infinitely repeated game. So also in each stage there is a discount factor such that the present value equals the future value times delta. So again, I already did this. Maybe $100 next year. If you deposit $100 in a bank, this money will be $100 plus equals 1 plus delta. That is a future value. What it means, future value 100, $100 will be the same as present value, if we multiplying dividing 1 plus interest rate. If we divide by $100 divided by 1 plus interest rate, then this number is representing present value with using future value, right? Then here delta is defined as 1 over 1 plus r. And we call this is a discount ratio. So from the future value, if we multiply 100, so that is future value, for example, if we multiply delta, then that is a present value. Okay? So there is a discount factor delta. Now think about the green trigger strategy, whether it is a Nash equilibrium. If that is Nash equilibrium, that's okay. So the pay-up, if the pay-up that deviated player gets smaller than the pay-up cooperating player, then even though a player decides to deviate from current Nash equilibrium, the pay-up that they can get is smaller than the pay-up when they keep playing Nash equilibrium. Then, no, not Nash equilibrium, green trigger strategies. And then, they will keep playing that green trigger strategy. And we are checking whether this green trigger strategy is a Nash equilibrium. So say that if one player keep cooperating, its pay-up is 9. Look at this. If both keep playing, Nash equilibrium, then they will get 9 and 9 forever. 9, 9, 9, 9 forever. However, because we have discount factor delta, each value can be compared to the present value by multiplying delta. So 9 plus 9 delta. And because, the 9 here in the third stages shows the value difference as much as delta, and it is applied one time more. So we should multiply delta one more time so that the present value of keep receiving 9 forever is 9 plus 9 delta plus 9 delta square and 9 delta third to this 3 and forever. We have a formula to sum up these numbers. That number equals to 9 over 1 minus delta. You need to check, there is a formula. It can be summed like this. Okay? If this number is smaller than when one player decide to deviate from the Nash cooperation, then no one will deviate from current, green trigger strategies. Now think about if one player deviate, and we add one more assumption. Suppose that another player perceives the player's betray after end stage. So think about it. This is the first stage, second stage is 3, 4, 5, 6, 7, 8, 9, and forever. They keep playing C and C and C. And maybe if one player decides to deviate from first stage D, if another player recognize that this player is playing D next time, maybe after second period and fourth period. Okay, and think about it. This player is betrayed player. All the player put C and C and C. At this time, when at the moment that all the player betrayed, all the player does not know that. So keep playing C. Maybe after 2 times, first time, this first term is passed. the second term is passed. So after 2 times of playing this D strategy, this player perceived that the first player betrayed. So, this player, second player, now does green trigger strategies or playing D forever because the first player betrayed, right? Because from for the first um, stages, because their payoffs are the same, we don't need to think about that. We don't need to consider these first 3 stages because their payoffs are the same. So think as if this first stage, when they are playing these stages, I mean, they can forget what happened in their history, right? So they would think this first stage as a first stage. So in this first stage, this player, the betrayed player will get 10 because it betrayed. Look at this. If one guy is playing cooperate and other guy is just betraying and denying, then that player will get 10, right? So from this first stage, this player will get 10. But after n terms, all the players, second player will recognize that this player, first player is already betrayed. Then just carry on that green trigger strategy. If this player play the green trigger strategy, then this second player will play deny forever to punish the first player. Then after that n times 5 here, 5 when both choose deny, 5 will be given to uh, these 2 players forever, 5 and 5 and 5. But even though they keep receiving 10 n times and after that 5 forever, because we have discount factor, it is actually 10 plus 10 delta to the n minus 1, 5 delta to the n, 5 delta n to the n plus 1, and like that. If we use the formula to make a sum of these numbers, we can get this. You can check the um, formula to find right to find the sum of these number series. Actually, we can get this, and this is the payoff when a player decide to deviate from Nash equilibrium. When both are playing green trigger strategies. So if one player has more value, one player has more value when they keep playing Nash equilibrium than deviating, then they can be stayed in playing cooperation. So if this holds, then they can keep playing cooperation. Look at this, because minus delta common here, we can get rid of this delta. What's remaining here is that 9, 10, 10 delta to the n plus 5 delta to the n. 9 will move to the right hand side, and if we do this, that is minus 5 delta to the n. If we move this term to the left, this 5 delta to the n is greater than 1. So from here, if we reorganize this term, we get this. So delta to the n, if delta to the n is greater than or equal to 0.2, then they will keep cooperate. And because both play green trigger strategies, so once delta to the n is greater than 0.2, then both um, they will this green trigger strategy will be a Nash equilibrium, actually SPE. So conclusion, from the criteria delta to the n is greater than equal to 0.2, then keep playing cooperation is a Nash equilibrium. This is very nice, right? Because even though we keep playing this Prisoner's Dilemma game um, with a finite number times, people keep playing deny and deny. They don't choose cooperation because they believe that this game will end in some times. However, if we keep playing this Prisoner's Dilemma game infinite times, then there is a way that people can um, keep playing cooperation once this inequality holds. And let's think about what it means. The higher delta is, right? Higher delta is this left-hand side term gets higher so that it's more likely to hold this inequality. And think about that. What does it mean, higher delta? It means world is stable because people think that future value is not too discounted to compare to the present value. Or future value is similar to the present value. Why? Because people think that world is stable. Future will be similar to, today and the past and so on. And also, people are very patient. They can, they can, because they are very patient, so that even though they are receiving some result in the future, it's fine for them. And also it also can be understood as that future is also very important as much as present. That's the meaning of the higher delta. Say differently, when the delta is very low, it means people think that world is it's not stable, unstable. And people are very impatient and think that future doesn't have any meaning, and they think that only present is important. If people think like that, they don't cooperate. They just try to focus on um, what they have and for themselves. So they don't care about the future. So that no one cooperate. Also, if we look at n, the lower n is that number gets higher, right? Because delta is less than 1, if we keep multiplying, that number is exponentially decreasing. So the lower n is the deception is easily confirmed. People are this society is very credible society, and each player can see another player is really abiding the rules they have, something like that. That is the lower end means. The lower end is the higher possibility that this player keep playing cooperation. Then cooperation becomes easier. So becomes easier. However, otherwise it is hard to make cooperation. Say differently, think about the cooperation. Cooperation, from the beginning, if people think that, if this game will end, then, basically cooperation is impossible. However, first, they should believe that they are playing this game forever. And they should believe that world is very stable and people are very patient. The future is also very important as much as present. Then they can have a cooperation. And also, so I mean, a society is very credible. If one guy is deceive another guy, I mean that deception should be easily confirmed by the society. That is the meaning of the law end. Then maybe cooperation becomes easier and it would be possible. In that situation, their payoffs are 9 over 1 minus delta each. Okay, so I mean the reason why I'm showing this result is that this result itself is very interesting, as you can see, and also I mean you can may apply this repeated game to some degree. If you have any question about this repeated game, you can ask me. And also there are many strategies that are different from the screen trigger strategies. This is just only one result we can get from the screen trigger strategy. Um, However, if people are playing different strategies, then also we can get to different results. Anyway, you may apply this idea in your model. Uh, Maybe not, but I think it will be helpful for you. I'm stopping here.